I think we understand that R squared tells you how good the prediction line is, just in general. R squared tells me that. Whether it's 67%, 94%, whatever. But is it possible, listen carefully, is it possible to have a high R squared value, let's say 92%? That's pretty good. Is it possible to have a high R squared value and one of the X values, let's say you're talking about X1, X2, X3, is it possible that one of those values, X1, X2, or X3, does not contribute significantly to that 93%? Maybe two of the variables are carrying the bulk of the weight, and the other variable just sort of along for the ride. Have you ever been in study groups? That's why I didn't really like study groups coming up in college. Have like 3 or 4 people in the group, right? And only 3 people are really doing like all the work. I know you've never experienced this before. And you all get a grade, A, and the other person in the group didn't really do anything. Have you guys experienced that before?
Yes.
All the time.
Yeah, all the time, right? And that's why I don't really, I don't know, I don't want to seem like I'm, better than anybody else. But if I put in my work, why are you getting a 93 just like I get a 93, right? So is it possible, I'm trying to use this for an example, is it possible to be in a study group and get an A and this person didn't really contribute that much? Yes. So that's kind of where we're going with this. We're going to look at, for example, you have R squared, but what we want to do is do something called test the significance of the overall model. And when I say test the significance of the overall model, I'm looking to see, yes, last week, Talia, okay. I'm looking to see if all members of, like, if every X member is contributing to this wonderful R squared number that we may have. Now, the R squared may not even be 90-something%. R squared may be 20, which lead me to believe that anybody contributed anything. Everybody deserve an F, right? But so in other words, what we're doing now is kind of the scene in terms of what the R squared value is. We're going to start calling out which one is not holding or carrying their weight. See? You're not carrying your weight. So that's the deal there. So let's write this. We're going to call this testing. And I'm sorry, I just have to keep going through different colors when I think they're strong. This weekend, I'm going to make sure I buy some more markers. So this is testing the overall significance of the model. Testing the overall significance of the model. Okay, so we'll start like this. We'll say sometimes we wish to see sometimes we wish to see how strong the relationship, okay, sometimes we wish to see how strong the relationship is between, sometimes we wish to see how strong the relationship is between the Y variable, and the X variables. Okay? Sometimes we wish to see how strong the relationship is between the y variable and the x variables. And as a reminder, I'm going to write this. We already know this. Y sub L equals, I'm just going to rewrite the general form of a regression multiple. So we have M1x1 plus M2x2. You know, we have that plus B, for example. Okay, so this is just the regular form. M1x1, M2x2 plus B. And then I'm going to write this. Now, so this is for, believe it or not, this is for the sample. I'm not even going to write that. But this right here, we haven't really talked about this, but this is like, say, for example, the data that we just looked at, appraised value. So essentially, we have, I think it's like 30 different addresses there on the left-hand side. They have like 2 Sycamore Street or whatever. So imagine if we had like 1,000 houses or whatever. So what we just did, in this case, we just chose 30 of them. So this will kind of be the formula like for the sample. But then we have a population that looks like this. Y sub L, Y sub L equals, it's going to look exactly the same. But what I'm going to do, I'm going to make a capital M1 as opposed to a lowercase m1, because this right here is going to represent like for the entire population, all of the houses there. What we just looked at in Excel was just a sample of 30. But in general, we're going to have this M1 X1 plus capital M2 capital X2 plus a big old B. So why am I bringing that up? Because eventually when we test, we start testing which variables are contributing significantly to the study group in a sense. We have to always refer to the population. And that's the same thing we did for ANOVA. For example, we had all these, I don't know, X bar, X bar, X bar. But when we did the test, we had to say like mu1 equals mu2. You always have to extend it to the population, right? So don't really worry about this right now in terms of the grand scheme of things. But I wrote this as capital M1 X1 plus capital M2 X2 plus a capital B, because eventually when we test, we're going to have to use these capital letters which stand for the population. Right? So now here's the question. So I'm going to write question. And as you're going along, just kind of keep thinking about the study group sort of like as a parallel to what we're doing. I'm going to say question. Which x variables have a significant relationship with y? Question, and it's a question mark. Which x variables have a significant relationship with y? Which x variables have a significant relationship with y? So this is going to be a two-step process. I'm coming from page, this starts with 339, and eventually, I didn't tell you, but we're going to eventually need your F table. And I think in the last pages that I said you're going to need tables. So we're going to eventually need F table, and something called a T table. And I think I put the T table in the folder for this week. So if you have those last couple of pages that I mentioned that you're going to need, those tables are there. And on page 339, at the bottom, is pretty much going to tell us how to do these steps, or at least give an idea for the steps. And it's going to be a two-step process. So let's say step one. Step one. Step one. Step one says, okay, I'm not going to deal with you individually yet, In other words, I'm not going to grill everybody in the study group yet. I'm going to with you all collectively first. Because if all of you all are trifling, then I know individually you're trifling, right? Right. So what I want to do is test the whole group first to see if there's anybody that sticks out, right? So I'm going to say test the entire set of x variables. Test the entire set of x variables to see if the group, okay, so this says test the entire set of x variables to see if the group has a significant, to see if the group has a significant relationship with y. So just kind of think, I want to know if in the group project, if everybody contributed equally or if nobody contributed at all. In other words, if I know as a group that nobody really did anything, then there was no need really for me to start looking at individuals, because the way the group turns out is telling me how everybody did contribute. Everybody didn't contribute, so then, all right. So what we're going to do first is test the entire set of x variables to see if the group of x variables has a significant relationship with y. Depending on these results, and this sounds familiar. This is like a ANOVA, like two-way. If you prove that there is interaction, then you don't have to go on to the next steps, right? So this is similar to that. Depending on what results we get here, will determine if we need to go to step 2 or not. Right? Now, when I test the entire set of x variables, it's going to look like this. We're going to essentially, I'm going to say strategy. Compare F test to F cutoff. We're going to compare F test to F cutoff. You're saying, wow, like ANOVA. By the way, I don't have time to do it right now. So where we're going here, well, I'll bring it up. It has to do with exam 1. Compare F test to F cutoff. So here's how, when we do here, you have to have some type of null hypothesis and alternative. So I'm going to say, in this case, A sub 0, right? And this is how it's always going to look when you try to test for the entire set of variables. Well, in this problem that we're looking at, appraised value, in the original problem, how many x variables do we have in the original problem?
In the one that we just did?
Yeah. Is it 3?
Yeah, 3.
Okay, so in other words, I'm going to start writing this in light of the problem that we have. So I'm going to say, okay, here we go. M land equals capital M age equals capital M room equals 0. What on earth? What on earth? So here comes this capital M again. Remember, what does a slope look like, just in general? Y equals mx plus b. I want to see if this makes sense. Y equals mx plus b. So everywhere, or like in this case, y equals m1 x1. M land X land plus M age X age plus M room X room plus B equals 0, right? We normally put M1, M2, but in our case, this is like the 1, the 2, the 3 here. What do I mean when I say these M's equal to 0? Think about the structure of a line, y equals mx plus b. If I say these M's are equal to 0, do you see how that shows no real relationship between x and y? Because see, if we write this, if I have like something like y equals 3x, just in general, I have like something like y equals 3x plus 5. If I have something like this, the fact that this number right here, which is a slope, is not 0, means that it's a bona fide line, right? If I put a 0 in place here of this m, then it kind of wipes this part out, and you have what results in like a horizontal line, all right? So if I'm saying m this equals m this equals 0, I'm essentially saying that there is no relationship. None of the variables as a group has a relationship with y. So I'm going to write it this way. In parentheses, I'm going to write what that means. Okay, just kind of follow me. So this means that none of the x variables, I want to go slow here. In other words, I have this. None of the x variables as a group, none of the x variables as a group have or has a significant, I know you may not be able to see this, that's why I'm saying it pretty loud. None of the x variables as a group have a significant relationship with appraised value. None of the x variables as a group have a significant relationship with, that's really getting too low, appraised value. So think about the study group. I'm saying before I investigate you one-on-one to see what your contribution was in the group, I'm going to deal with you guys as a group in general, right, as a whole. And if need be, then I'll go to the next step of dealing with you one-on-one. So our h of 0 always looks like this when we're trying to compare the entire set of variables. This is step 1. H1 looks like this. I'm sorry, h of 0 looks like this. And H1 says, I'm going to have to write this over here. H1 says at least one of the slopes, and I'm just going to write capital M, at least one of the m's does not equal to 0. At least one of the m's, one of these m's right here, at least one of them does not equal to 0. And in parentheses, I'm going to write this. So you have this in interpretation. This says at least one of the x variables has a significant, it's basically the same thing over here, significant relationship with appraised values. The appraised value. Now, I understand you probably can't see this here, so I'm going to say it again. So here's my strategy. Compare F test to this. Now, h of 0 says m land equals m age equals m run. In other words, all of them equal 0, which is essentially saying none of them have a significant relationship with appraised value. And then over here, the opposite of that is saying at least one of these m's is not equal to 0. When it's not equal to 0, what does that mean? Oh, then it does in fact have a strong relationship with appraised value. So I don't know if that seems counterintuitive because you're saying it's not equal to 0, right? But when m is not equal to 0, that means it's going to fit in terms of a regular line, m of y equals mx plus b. Yes.
What does it say, Professor? After the m on the side, it says m something is not equal to 0.
Yeah. So it says one of the m's, and I just put apostrophe s. In other words, one of the m values, one of these m values is not equal to 0. So I just put an apostrophe s to sort of like m, like how you see like M&Ms. So it's like one of the m's, one of these. Is everybody at least okay with this, with the general setup of this? Yes.
So for the first one, it was none of the x variables as a group, but for the second part, is it at least one of the m or x values?
Yeah, that's an interesting question because although we are making the decision about x's, we're doing the test on the m's in front of it, which is the slope. And so depending on what results we get for the slope, that's going to affect x's. So it essentially, again, how does the regression equation look? The regression equation looks like this. Y equals m1x1 plus m2x2 plus b. But when we're doing our test, we're gathering information about the slopes. And then once I get this information on slope, it's going to tell me about the x eventually, right? So we're doing a test on m, which is going to give us data on x.
Okay, so for the H1, the interpretation part, or the part where you said it in words, it's an M. The M values, correct? Not X.
No. It's correct. So
okay.
We're doing the test on the slope, but in terms of results, it's going to still tell us information about that x variable that slope is beside. So just like we have these m's equals 0, but in the here we have none of the x variables as a group has a significant relationship with the appraised value. So I know it's going to take some getting used to because you're saying, well, you're doing m, but as we find information about m, it's going to tell us information about the x that's beside it. All right? Okay, all right. So how do we do this?
Professor, read the H1.
At least one of the m's is not equal to 0. Yeah.
And then what does it say? At least, and then it's a parentheses.
At least one of the x variables. At least one of the x variables has a significant relationship with appraised value. Okay, so let's move on with this test here. We're still in step 1. Now, go to your results. Go to your results in the regression where we have all 3. I guess it's the first one that we did out of all of them. Go to those results. Eventually, we're going to draw something like this. This looks familiar. This is the F distribution, where the hump is on the left-hand side. We need to figure out the F test and the F cutoff. Go to your results there. We ran the regression. Do you see, I'm going to try to do this without sharing my screen. Let's see. Glencoe. We need all of them, x1, x2, x3. If you can find those results, see if you can locate what you think may be an F value. You see anything that says F there?
Yes.
What there? What do you see? What value?
So under like ANOVA, it says F is it would be 18.21.
Very good. Very good. Does everybody see that? You have to go back to the original printout that you did first with all of the variables, x1, x2, and x3. Does everybody see that F value where it says 18.2?
Yes.
So then that's going to be my F test. Okay, so F test will always be given in that printout. I'm going to say F test equals 18.2 or 0.21, I guess, or something like that. That's always going to be given. Now, I just need an F cutoff, and I'll be good to go. F cutoff. So once I get this F cutoff, that's going to be the value that I put right here. And I have to see where the 18.21 falls on that spectrum. Acceptance region here, rejection region right here. Now, the F cutoff we're going to use, if you look at you're just going to go around knowing this, but I'm going to try to show you. And as a matter of fact, everything we're doing here on page 340, look at page 340 and page 341. The cutoff here is going to be F of, so we're going to use K, comma, N minus K minus 1 and alpha. So this is F. Let me make sure you guys kind of see here. So the F cutoff is going to be F, K here, N minus K minus 1 for a certain alpha. Now, I don't know if it tells us in this problem what alpha is, but we'll use 0.05. Does it mention anything about alpha in this problem? I forget. Yeah, Katarina?
Professor, can you, it like broke up for me. Can you say what K equals, what F cutoff is again?
Oh, yeah, sure. Yeah. So the F cutoff is F, and then we have K here, and then comma, then N minus K minus 1 for a certain alpha level. All right. Does it say what alpha? Does it say what alpha should be in this problem? The one we're doing on the handout. Does it say 0.05 or does it not say anything?
I think it says 5%.
Okay, good. All right. So that's just letting me know what side of the table I'm going to use. So we're going to have 5%. Now, what is K in our problem, in this specific problem? What is K in this specific problem? How many variables do we have? 3. So we're going to have 3, comma. What is N in this problem? Take a guess. What is N in this problem? Get the data on the Excel sheet.
It's 30.
Okay. Where are you getting that from?
So if you look at the summary output, it says regression statistics, and at the bottom it says observation.
Oh, okay. Yeah, I was going to count, but yeah. So it's yeah, very good. Everybody see where that is in the results. You see the observations 30. Yes. Or what you could do is count how many data points you have in the entire problem. Right? So we have 30 addresses. 30 addresses. You can count it, or you can get it straight from the table there. 30. Okay, so we have 30 minus what? Our K again is
3.
And minus 1 for a certain alpha, 0.05, equals F of 3. What is this? 30 minus 3 minus 1. Is that 26? It's 26. All right. Now, get your F table. Get your F table and see what our cutoff value is. Make sure you're on the right side. So you need to be using 0.5%. And somebody let me know what that is. What is that cutoff value? Everybody should have an F table. So you're going to go over 3 and down 26. What is that?
It would be 2.98. 2.98.
Yep, that's it. 2.98. 2.98. So then this value here becomes this value right here, 2.98. That's the F cutoff value, 2.98. That separates acceptance region from rejection. So where does our F test fit? In the acceptance region or the rejection region?
Acceptance.
No. See,
No,
here's a F right here. Yeah, see, the F test is 18.2. So 2.98, so go in the regular, so it's over here somewhere, right? 18.21. So yeah, so that's going to be in the rejection region. So what does that test include? Remember what A sub 0 is, because see, this decision is going to determine whether we accept A sub 0 or reject A sub 0. What do you think we're going to do here? Are we going to accept A sub 0 or reject? Okay. So we're going to have something that looks like this. Let's write this. Since our F test equals 18.21 is in the rejection region. You can say what it is greater than 2.98. We reject A sub 0. What does that mean? What does that mean? This means what?
That none of the X variables as a group have a significant relationship with the praised value.
Well, let's see. Are we accepting A sub 0 or?
Oh no, so at least one of the X variables would have a significant relationship.
There we go. Yeah, because see, we're rejecting A sub 0, which means now we fall in the category of we have to consider A sub 1. We're going to accept A sub 1. So this means at least, and you can just write it verbatim from H1, at least one of the M's. You know what? I'm not going to write it that way. I'm just going to write words. At least one of, so what you can do is write everything that we have in parentheses right here. At least one of the X variables has a significant relationship with appraised value. And my mark is fading away. Okay, so I'm going to read this again. So let me slow down. Does everybody understand where that 18.21 comes from? It literally came from the result of your regression using all of the variables. So when we get to here, I know what we did earlier this morning. We broke them up, these two. When we go to test an overall model, we've got to go for the model that has all of the variables in it. Yes? So that information is going to come from the F in the printout or the results for all of the variables. Now the F cutoff is going to come from the table. So in your notes, just make sure you know, it's K then N minus K minus 1 for a certain alpha. Yes? Then I do what I normally do with the F distribution. And this is just the conclusion of step 1. So this concludes step 1 right here when you write this information right here. If we would have accepted A sub 0, and we didn't, if this F test would have been over here, we would have accepted A sub 0, and then that would say none of the x variables as a group has a significant relationship with, value. If you accept x at 0, then you stop the whole process. You don't go to step 2. Because if all of them as a group are equal to 0 in terms of the m, then I don't have to see which one is significant, because it's saying all of them equal 0. See? None of them have a significant relationship. So generally, when you accept x at 0, that assumes that your R squared is pretty low, 30-something%, right? None of them really have a significant impact. So let's just stare at that for a moment. Let's stare at that for a moment. Because we just concluded that at least one of the x variables, we tested the m's, but we're making conclusions about the x's, right, that they're beside, the m1, x1, m2, x. So now what do you think we have to do? If we concluded that at least one of the variables has a significant relationship, what do you think our task is now? Yes, who is it?
This is Talia. I just have a question.
Yeah.
So it's saying at least one. Does that mean that it could be all 3 affecting it equally, or does this mean that some affect it more than others?
Yeah, good question. That means that x1 could have a strong relationship with y. x2 could have this. So in other words, it doesn't necessarily have equal effect on, in terms of a significant relationship. It doesn't mean that they necessarily have the same effect, but they could have a significant relationship with y, right? And, were you saying, well, what do you mean by significant? How significant is significant, right? It doesn't mean that this one has the same effect as this one has the same effect as that one, but as long as we have some wiggle room, namely some 5%, like normally we identify some kind of 5% threshold, then if it fits within that threshold, then we're going to say it's going to have, it will or will not have a significant relationship. And that's kind of what we're going for step 2. The only thing this says here is that we know at least one of them does have a significant relationship with appraised value. And I don't know if the answer really makes sense, but I think when we go to step 2, it should clarify it. But the answer I was kind of trying to prod you guys for was to say, well, if at least one of the x variables does have a significant relationship, then our task is to go to the next step to see which ones do and which ones don't. So step 2, in this case, we're going to have to do 3 separate tests. Which makes sense. If we have 3 different explanatory variables, we have to do 3 separate tests. If we go to step 2, we have to do as many tests as we have x variables. Let's say step 2, and we'll finish up.
So you only go to step 2 if you reject h sub 0, right?
There you go. Exactly. If you accept h sub 0, then you stop. There's no need to find out which ones have a significant relationship, because step 1, you've just proven or disproven that all of them together have no significant relationship as a group. And we'll assume if we prove that all of them have no significant relationship, then one of them, when you look individually, they won't either. Okay, step 2. Step 2. Let's see how we're going to write this. That's that. We're almost done. And this is coming from page 342, if you want to follow along with what we're doing here. Page 342. Let's say we test each variable separately. We test each variable separately to see which has a significant relationship. We test each one separately. So now this is like doing group work. We're saying, okay, I've just proven that one of you guys in this group are just around. You didn't carry your weight. You can run, but die. Right? So essentially, when we rejected A sub 0, we're saying, okay, it's not the case that everybody in the group just didn't do anything. It's just that one of you just didn't carry your weight. So now to figure out which one is not really contributing to R squared yet.
Can you read what it says after separately too? I can't see what it says at all.
Separately to C, which has a significant relationship. All right, so let's say strategy. Perform individual I want to write that letter T. Perform individual t-tests. Perform individual t-tests. That's kind of faint there. You know, thank goodness for the recording. You guys can sort of go back and listen to it. But perform individual t-tests. Essentially, you're going to compare a t-test to a t-cutoff. T-test to a t-cutoff. Now, watch this. I'm going to tell you how these are going to go. So the first one, you're going to have this, A sub 0, capital M, land equals 0. You see before how we had all as a group, M land equals M age equals M room equals 0 all together. Well, here what's going to happen is that I'm just going to look at them individually. A sub 1, M land does not equal 0. That's one test. Now, what does that say? Essentially, what this says is, I'm going to look up A sub 0. Land acres does not have a significant relationship with appraised value. Okay, let's say that again. Land and acres does not have a significant relationship with appraised value. Okay, this again. So this says M land equals 0. And what this means in words, see how I'm going one by one? Land, that variable land. So remember, land is the X variable. And I'm looking to see what the slope is doing beside land. Right? Land does have a significant relationship with appraised value. So down here, when I say it's not equal to 0, land, the variable of land, does have a relationship with appraised value. So let's just stop just for a second. Land, the variable of land. I mean, I think you guys kind of see where this is going. I'm going to be going one at a time now to see which one is contributed, because even though you can have a high R squared, it's possible that one of these variables is not holding it to. So what this says is land does not have a significant relationship, and then when I say it's not equal to 0, that means land does have a significant relationship. It's kind of counterintuitive, because you would think when you say something's not equal to 0, then that's a bad thing. But the fact that this is not equal to 0 says it does have a significant relationship. So I'm going to do this one here to model the process, and then I'm going to have you do the other two. In fact, leave some room to solve it, and go ahead and write what you think are the other two tests that you're going to do. Right? This is the first one, m land equals 0. So just leave some space and do the second one based on what you think it should look like. What's that? Age? I think it's age. M age equals 0, blah, 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 blah. Then the last one, M room. You're going to do 3 separate ones. Then I'm going to come back and finish this one, and you're going to do the same thing for the other two.
So you want us to go write all those out right now?
Yes. You have, but you want to leave some space. So like number 2, in other words, there are going to be 2 more of these statements right here. A sub 0, A sub 1 for age, and then A sub 0, A sub 1 for room. If you want, just follow this same pattern in terms of what it is in words, but just replace land with age and then room. Age and then room. Okay. You still may be writing, but that's fine. I think you kind of get the flow of it. Let's do this one here, and let's get ready to call it a day. Let's test this thing right here. Just for space, I need to erase this just for a second. You guys remember in Stat 222 doing like a t-test? It leaves the picture. Do you know what a t-distribution looks like? It looks similar to the what? Yeah, it may be too blurry, so just kind of listen to what I'm saying. We have to make do. I'm going to buy some more markers this weekend, but just kind of follow as best you can. The t-test mimics what distribution in terms of the picture? Does it look like an F distribution? You guys remember? It looks like this. Bell curve. Like the Z. Okay. So the F distribution that we do for step 1, the hump over the left side and kind of trails off like that. But when you get to step 2, I'm only going to be involved with t-tests, which means that eventually for step 2, I need to see 3 separate diagrams. This one will be for this one, another diagram will be for the second one, and another diagram would be for the third one, like M age and then M rooms or whatever. So I'm going to show you how to do this here. All right. I need a t-test statistic and a t cutoff. Now, let's start with the T cutoff. Let's start with the T cutoff. Because the same T cutoff that I have for this one here, the first one, is going to be the same T cutoff that I'm going to use for the second and the third one. Yes? So again, if you can, draw this same basic diagram for the second one and the third one. It's a regular bell-shaped curve. And the only thing with a T distribution is that you're just making decisions based on a smaller n value. It's like a small n. Don't worry about that. Okay, so draw this for this one. For the second one, draw another one. And then for the third one, draw another one. Look just like this. My T cutoff is going to look like this. And essentially, this page 343, yeah, you can kind of see the setup of those there. Yeah. Okay, so my T cutoff is going to look like this. T n minus k minus 1 for a certain alpha. So my T cutoff is T n minus 1 for alpha. We did this calculation earlier. What was this T of what? What is n minus k minus 1 in our problem? It was 30 minus 3 minus 26. I think it was 26 that we did F.
Yeah, it was 26.
26, okay. And I don't know if they specified. Now, this is in the problems that we're doing. I think we moved on to, what number is this? Is this number 3 or 4 in the handout? Okay, if you reject, use individual t-tests to determine if there's a significant relationship. Okay, good. So this is number 4. And I didn't say, but we're going to alpha is 0.05. 5% level. So we'll assume whatever it is in number 3, it'll be the same for this. So everybody grab your T table. If you don't have it, I put one in the folder for this week. You should have your own.
Is the T like T equals n minus k minus 1 or like T times?
Oh, it's a subscript. Right. So it's like, ooh. So it's like T and then, okay, so you know what exponent looks like, right? Like T squared. So this n minus k is like the opposite of that. It's like a sub T sub n minus k minus 1.
So like, what does that mean?
Well, yeah, so that's, yeah. So in other words, you see how we did before? We had F, we had 3, 26, so we went over 3 and down 26. So this is what's called degrees of freedom. It just tells you what your cutoff is going to be. So the same thing for.
So we're not multiplying the T with anything.
Oh no. Yeah, so this is going to be alpha equals 0.05. It's just telling you where to go in the chart to get your final answer.
Oh, okay.
Yeah. So say for example, does everybody have their T table? Look at your T table. It's page 654. You can use the one that I put on Blackboard. So all this is go to the T chart and find alpha, and we're going to do two tails, not one tail. So 0.05, and then go down to 26. Go down 26. And I'm not going to multiply it by anything. What value do you guys come up with for your cutoff? What is that?
2.056.
I think that's right. So again, we always going to go to two tails. You're going to go over to your alpha level, 0.05. Yeah, I think that's right. And then go down 26. Down 26. 2.056. So this equals 2.056.
Can I ask a question?
Yeah.
Where are we getting the data from, like the top part? I'm confused about that.
What top part?
So like I know like the left part, like DF, we're gonna use 26 because that's what we got from the F cutoff equation. But then like what does that part of the T chart mean?
The top part is letting you know where the rejection region is going to be. we didn't go over it in this class, but sometimes you can do problems that are called one-sided hypothesis tests, and sometimes you have two-sided or two-tailed. So two-tailed just simply means that the rejection region is in the right-hand side and the left-hand side. So in these problems, we're always going to go to two tails at the top and go to the alpha of 5%, which is 0.05 there.
Oh, okay. All right.
See that? So when I plot this, let's see, there's the middle. So this means that here and here, we have some rejection right here, and then some rejection right here, two tails. And in these problems, we're always going to use the value that corresponds to two tails as opposed to one tail. So here's one of our cutoffs, 2.056. What's another cutoff? Think carefully. Look at it.
Negative 2.056.
Yes. See, when we get our cutoff in these problems, when you go to step 2, it's always going to be two values, the positive version of that and the negative version of it. Positive version and the negative version. Now go ahead and draw the same picture for the second one and the third one that you did. Because the cutoff is going to be the same for this one. This one here probably should look like MH equals 0. And then H1 should be MH not equal to 0. Right? But this picture here is going to be the same picture for this one and the third one. So everybody go ahead and draw those for there. And we're pretty much almost there. We're almost there. So now,
So you said that it's the same for the first and the third one. Is it not the same for all three of them?
yeah, it's the same for this one, and that one.
Okay.
The first one, the second one, and third one in terms of the cutoff. So as long as you know this part right here, K minus 1, and the alpha level, you know, I make sure I give it to you 0.05, and you should know how to get the cutoff points here. We're almost there. I have all my cutoffs. Now I just need to find my t-test statistic. Go back to the data. Go back to the Excel sheet. Go back to the Excel sheet. Will you use all three variables? Let me show you here. All right, so this is the data here from the very first regression that we did. Where do you think I would find the t-test statistics?
There it says
Stop.
that.
There we go. Okay. In particular, I won't worry about this one. Because see, that's for the intercept. But I do have these separate ones here that correspond to the X variable that they're beside. So say, for example, land, acres, I use that as my t-test statistic. Age, I use this one. And rooms, I use this one right here. So say, for example, that's 4.38 for land. 4.38 for land. So here, where does 4.38 go on this table? Let's go over here somewhere. 4.38, because see, here's 0 right here. So I go, you know, as I'm going this way, 1, 2, 3, 4 here. And then this way, -1, -2, -3, -4 over here. So there are two opportunities for it to fall in the rejection region. So here, it falls in the rejection region. So what does, without writing all this stuff down, you know, since blah, blah, blah falls in the rejection region, we reject x of 0, and we make what conclusion about the first one? What do you, and I erased what was in parentheses, but based on these results right here, what does that lead you to believe about land acres as it relates to appraised value? We reject So what does that mean in words?
It doesn't have a significant relationship.
Are you saying it does or does not?
No, it
Doesn't-
would have a relationship.
It would. Oh, okay, because we end up with it being over here. See, this is the rejection region right here. So we reject this, which means that we accept this. And what does this mean? That the variable of land does have a significant relationship with appraised value. So this variable did its part in the group assignment. Yes? Yes. So now for the other two, you're going to have different values that you're going to be seeing if it's in the acceptance or rejection region. Look real quick at those other numbers. Does any of them fall? What is age? Let's see. So this is still 2.056. This is negative 2.056. Huh?
We reject all of them because none of them fall within the acceptance range. Yeah.
Okay. Okay. So what is the T statistic for the second one?
Negative 4.07.
Okay, so it's over here.
Yep.
Here, negative 4 point. Okay, what's the third one? What is room?
2.9.
2.79?
Yeah.
Okay, so in the third diagram, it's also over here. Oh, okay. So again, just in the interest of time, I'm not going to write those long paragraphs, but perhaps next class I will. Since blah, 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 blah falls in the rejection region, just make sure, so that you don't get lost, you kind of write the part in parentheses that kind of tells you about it. But yeah, I think this is the case where this value has a significant relationship. This also has a significant relationship, and the other one has a significant relationship. But it's not always going to be that way. It's not always going to. You have to test, because one of these could just be along for the ride and not doing its part in the group assignment, as it were. Okay. So it turns out here everybody is contributing to that R squared value. Not necessarily equally, and I think that was maybe Katarina's question. Not necessarily they're contributing equally, because see that 4.38, and that was a negative 4 point something, and then this was like 2 point whatever. So it's not necessarily saying that they're the same number, but they still are carrying their fair share in terms of what the cutoff value is. I don't know if that really makes sense, but